In this part 3 of the Exam 2 review, we're going to go ahead and talk about partial fractions and more generally how to integrate rational functions. As we'll see, and as we have seen before, just because we have a rational function doesn't necessarily mean we have to do partial fractions. And in fact, this first example demonstrates that, okay? So we have an integral here, x squared plus 1 over x minus 1. And we see the fraction, we might be tempted, oh, I just need to do partial fractions. Well, you might see a couple of things wrong here. First off, the denominator is only x minus 1. That's only one thing. Okay, so there's not really much to do. Okay, and second, notice that the numerator, okay, is large. The degree of the numerator is larger than that of the denominator. Okay, this is a top-heavy function. Okay, this is top-heavy. Okay, what that means is the degree of the numerator is larger than that of the denominator. So we have to do long division first in order to force this to be a proper rational function, meaning one whose degree of the numerator is lower than that of the denominator. So we have to do long division first. Okay. Now, to do long division, okay, remember, please watch that part of the video in the partial fraction section to remind yourself how long division goes. We're going to go ahead and set up our usual long division. I'll leave a space here, okay, for the linear term divided by x minus 1. And remember, for the traditional polynomial long division, we just go ahead and look at the highest order terms and do the usual long division steps. Do to divide, multiply, subtract, repeat. Okay? So when we look here, x squared divided by x is just x. Multiply here, we get x squared minus x. I'm going to go ahead and subtract that. And what that gives me, let's move that there. What that gives me, we have x squared minus x, which is 0. 0 minus negative x, which is just a positive x. We bring down the 1. Do the division again. X divided by x is a plus 1. Multiply. Okay, so we have 1 times x minus 1 is x minus 1. Subtract. And then 1 minus negative 1 is a 2. Okay, so what we have here, okay, is that our original integral here, x squared plus 1 over x minus 1 dx. Okay, remember that when we do this long division, okay, we get the quotient, which is its own thing, so x plus 1. And then the remainder, we're going to add the remainder over the divisor. And now take a look. The first two terms are very easy to integrate, as is the third. There was no partial fractions to be done here at all. Okay, so when all is said and done, okay, we use our power rule here. And then, of course, our base integral for the logarithm. Okay, don't forget your absolute values here. And we're done. There was no partial fractions needed here. Okay. There was no partial fractions needed. Now, I want you all to please go back and watch those partial fractions video series, okay? That describes how to do the partial fractions decomposition and in advanced examples when to actually do the partial fraction decomposition. Okay, now let's move on to our next one here. Okay, this is an example of one where we have to do a partial fraction decomposition, okay? We have 1 over x cubed minus 2x squared plus x in our integrand. Okay, this is bottom heavy. Okay, and so we need to set up for partial fractions. So what we need to do is to first factor the denominator, okay? So we're going to factor our denominator here. I'll do that off to the side here in this pink color. So we have x cubed minus 2x squared plus x. Note that I can factor out an x as a GCF. So we get x times x squared minus 2x plus 1. Okay. And now, okay, notice that the inside part is actually a perfect square. We have x times x minus 1 squared. And now take a look. We're basically ready to go for partial fractions. So we go ahead and set up the recipe, okay? We have 1 over x times x minus 1 square. I have one distinct linear factor and one repeated linear factor. Okay, x is a distinct factor that gets its own, okay, a over x. And then for the repeated linear factor, we have two copies. So b over x minus 1 plus, once again, c over x minus 1 square. Okay, remember that for the repeated linear factor case, anytime you have a repeated factor, you have to count up. Okay, keeping the numerator pattern the same. Okay, now we do our usual thing. We go ahead and clear the fractions. Okay, so I'm going to write this here. Okay, though please watch the recipe and the method to see how to do the decomposition again. Okay, we're going to go ahead and multiply both sides of this by x times x minus 1 square. Okay, so on the left-hand side, we just get 1. And on the right, we have a times x minus 1 square plus b times x minus 1. Okay, and then plus c times x. All right, so now we're set up to find these coefficients in whichever way we want. We can set up a system of linear equations by equating coefficients, or we can use the so-called cover-up method. So remember, for the cover-up method, which I think is probably the most straightforward here, we go ahead and choose clever values of x to substitute on both sides of our identity, okay? And we solve for the corresponding a, b, and c. Okay, so we're going to go ahead and select values that make sense here. For example, x equals 0 is a nice choice here, because if I plug in x equals 0 on the right-hand side, and technically on the left, but there's the left-hand side is independent of x, so we don't have to worry about it here. If I plug in x equals 0, notice that the terms containing b and c vanish. Okay, and so all I have left here, 0 minus 1 is negative 1. Negative 1 squared is a positive 1. We get that 1, let's do this in black here, okay? Get that 1 is equal to 1 times a. And so this clearly gives us a equals 1. Now we choose another clever value of x. Here, x equals 1 is a pretty good choice. Again, on the left, it's independent of x, so we just write down 1 equals, okay, well, what's next? Okay, we have 1 minus 1, which is 0, okay, squared is 0. So any term that has an x minus 1 will vanish, and that just leaves us with, well, 1 times c. So c is equal to 1. Now you look at this and you might say, like I've probably said in the other video, okay, well, I've run out of clever x values. This is where you can choose whatever you want. So I'm going to go ahead and choose x equals negative 1. You could choose whatever other convenient value of x you like, maybe 2 even. That's probably another good choice. But for x equals negative 1, let's write down what we have. We have 1 equals a times negative 1 minus 1 square plus b times negative 1 times negative 1 minus 1 plus c times negative 1. Well, I already know a and c. B is the only thing that's unknown that I solve for, okay? So when we tidy this up, okay, negative 1 minus 1 is negative 2 squared. That's 4. 4 times a is 1. Okay, plus negative 1 minus 1 is negative 2 times another negative 1 is a positive 2, so 2b. And then minus c, okay? Well, c is 1, okay, so minus 1. Okay, well, now we just go ahead and collect our like terms. Okay, so 4 minus 1 is 3. Okay, or you can even cleverly do this here. So add 1 to both sides, you get 2 equals 4 plus 2b. Okay, subtract 4 on both sides. Okay, so we get negative 2 equals 2b. That means b is equal to negative 1. Now look at this, okay? I have a, b, and c. I can go ahead and plug this into my recipe, all right? So I'm going to go ahead and copy this over, all right? Be a little careful here. So we copy, we paste, all right? And now let's write down what we're going to be getting here. So originally we had the integral of 1 over, let's see, x times x minus 1 squared dx, okay? Well, that's equal to the integral of all this stuff. And now we just replace a, b, and c with the values that we have found. So we found that a was equal to 1, c was equal to 1, b was equal to negative 1. And all three of those integrals are very easy to do, okay? We just use our base results here. First integral, that's going to be natural log of absolute x. The second integral will have minus natural log of absolute x minus 1. And the third, okay, remember our base integral. If you need to, do a u substitution on that one if you need to. But this one, we just use the power rule. This just ends up being minus 1, excuse me, over x minus 1 plus a constant. Okay. So this one was an example where we actually had to do the partial fraction decomposition. Okay. We followed the recipe, did the algebra, and here the only calculus that we did was here. Okay. Remember, of course, again, when you integrate 1 over x or 1 over any linear function, okay, when you take the antiderivative, you need the absolute value bars in the logarithm. Okay. Technically, you're supposed to do that. Okay. There are some cases where we can skirt that. This is not one of them. Okay, let's go ahead and take a look at our last partial fraction here. Okay. And I just have to make sure I have the right thing on my notes here. Here we go. All right. So we have this one here, 1 over x cubed plus 4x. Okay, this is another bottom heavy one, so we're going to go ahead and set up for partial fractions. Okay, note that I can factor the denominator by pulling an x out. I have x squared plus 4 as the remaining factor. Now, x squared plus 4, okay, if you recall, this is an example of an irreducible quadratic. Okay, all sums of squares are irreducible quadratics, okay? That means that you cannot factor these over the real numbers. If you try to factor this in such a way, well, you actually get complex numbers out of this, and we're not going to worry about complex numbers for the moment here. Okay, now, of course, you're free to do that, okay? It doesn't really change much, but let's just stick to the real number system here. So we're going to go ahead and set up our recipe here. So we have 1 over x times x squared plus 4. We have one distinct linear factor, a over x. And then for the irreducible quadratic, okay, at worst, the numerator is linear. So bx plus c over x squared plus 4. Now we do our usual thing. We go ahead and take this, multiply through by the common denominator, so x times x squared plus 4 to clear the fraction. And I have 1 equals a times x squared plus 4 plus bx, well, let's be careful here, bx plus c times x, okay? That's just done by multiplying through, distributing, doing all that good stuff, okay? Now, once again, you can go ahead and set up a system of linear equations, okay? Or you can use the cover-up method. Cover-up seems pretty good here. Let's choose the lazy value x equals 0. I think that's a good place to start here. So if x is equal to 0, again, the left side is independent of x, so we have 1 equals, well, we'll get 4a, and guess what? The second term is just 0. And so this tells me that a is equal to 1/4. Okay, let's fix that there. All right. Now, what do we do for b and c? We still have like these two undetermined coefficients. Well, we can actually go ahead and set up a system of two linear equations, okay? It won't be too bad. So when x is equal to 1, okay, we'll go ahead and have 1 on the left equals, well, 1 plus 4 is 5. 1 squared is 1. Okay, so I have 5a. Let's just write out what we get. Plus, x is 1, so we'll just have b plus c. Okay. And of course, a is equal to 1 over 4. So when I multiply these two, I just get 5 over 4. Now, the next value I'm going to choose is x equals negative 1. So again, on the left-hand side, we get 1, and then equals what? Well, negative 1 squared is 1, plus 4 is 5, times a, which is 1 over 4, that's 5 over 4. Okay, remember, we're just replacing x on both sides here, okay? It just so happens that the left-hand side was independent of x, okay? So look out for that in your practice. Now, here, x is equal to negative 1. So let's go ahead and write this out in full. We have b times negative 1 plus c times negative 1, okay? And now we're going to go ahead and tidy this up a little. Okay, notice that on both these equations, I can go ahead and subtract the 5 over 4. Okay, so when I do that, I'll have a negative 1 over 4 equals b plus c for the first equation. And for the second equation, I have negative 1 over 4 equals, well, let's take a look here. I have negative b. Okay, I have negative b plus c in there, and I can multiply the negative 1 through. Okay, take a look at what I get here. When I multiply the negative 1 through, I get b minus c. Okay, and this is actually a very easy system of equations. I can use substitution, okay, but of course, elimination here is probably like the way to go here. Okay, so take a look at what happens. If I add these two equations, well, negative a fourth plus a negative 1/4, that's a negative 1/2, equals b plus b is 2b, and then c minus c is 0. So what do we get here? We get here that b is equal to negative 1/4 after we divide by 2. And then when we plug in, we get that c is equal to 0. Okay, so now we have our weights, we have our unknowns, and now we just go ahead and plug back in. So we're going to go ahead and take this part here. We're going to go ahead and replace with everything that we found here. Okay, and trust me, this is not too bad, all right? So our integral. Wanted to look at the integral 1 over x times x squared plus 4 dx. That's going to be equal to this integral. Slide that over. Okay, the integral of a, well, what did we say a was? A was a fourth. Okay. Plus, now bx plus c. Well, c is 0, so that term can go. And b was minus a fourth. And now this integral is so much easier. Okay. The first term, that's our base integral again, 1/4 times natural log of absolute x. But how about the second? You can attack the second in a couple of different ways. Probably the more natural is the substitution here. Okay, just go ahead and set u equal to x squared plus 4. So du is equal to 2x dx. Okay, now remember in u substitution, I want to try to play for the match. Okay, so if I divide both sides by 2, I get 1/2 du equals x dx. And folks, that's second integral, which I'll keep in that same color. Okay, if I pull the minus 1/4 out, okay, get minus 1/4 times the integral of, well, x dx is 1/2 du, so 1/2 du over u. And folks, our base integral again. Okay, if we do finish out the work here, okay, we'll have a minus 1/8 natural log of absolute u plus a constant. Okay, and now we just back substitute. Okay, 1/4 natural log of absolute x minus 1/8 natural log of absolute, what was u? X squared plus 4 plus a constant. Now, technically speaking, you don't really need the absolute value on that second part there, but to keep it kosher, go ahead and put them there, all right? Now, you can also, in fact, if you're very clever, okay, if you notice that you have the sum of squares here, this x squared plus 4, you can go ahead and use a trig substitution. Which one? Well, I'll leave that for you to decide and see if you can reverse engineer this result by using a trig substitution. Okay, so that's it for integrating rational functions, and that's the last integration technique that we have. Okay, in part 4, the final part here, we're going to talk about improper integrals, and we're going to combine all of these techniques together, plus use some estimation to see if we can decide if an improper integral converges or not. And I'll see you in that next one.